Uh, Today's discussion for critical speed of simply supported rotor with one side overhung. This is another important topic for discussion. So previously I have seen the critical speed for simply supported rotor only, and in this section we'll see the simply supported rotor with one side overhung. As I said, this is a general method, so we can calculate the critical speed, multiple critical speeds with accuracy for one side overhung. These are the some feature or consideration that rotor is considered flexible. That means bearings are considered rigidly supported, and two bearings are shown here, and one side is overhung. And as I said, this will provide we can calculate the critical speed with first critical as well as higher critical speeds. And another assumption is that moment of inertia of disk is not considered. That means mass of disk is considered as a point mass. With that assumptions, we'll see how we can calculate the critical speed of rotor. Main broad discussion for this section is theory part, procedure part, and finally calculation through an example. So theory part, this is first section. This is general methods for critical speed. As you see, this is a overhung, so it has two shaft section, that is span 1 and span 2. A span 1 is between two bearings and a span 2 is between one bearing and another friend. As I said, it has been divided into station 0 to 10 for span 1 between the bearings, and from station 10 to 20 is for span 2, that is overhung. Shear force, bending moment, slope and deflection, we have already seen in the previous video how to derive this, so in this section we will not derive it again. Shear force at station N can be written as Vn is equal to Vn minus 1 plus Mn minus 1 omega square Yn minus 1. This is for general equation for shear force. Bending moment at station N is equal to Mn is equal to Mn minus 1 plus Vn into Ln. Slope at station N is equal to theta n is equal to theta n minus 1 plus beta n into bracket start mn minus 1 by 2 plus mn by 2 bracket close. Deflection at station N, Yn is equal to Yn minus 1 plus theta n minus 1 into Ln plus beta n into bracket start mn minus 1 by 3 plus mn by 6 bracket close into Ln. So these are the general equation for shear force, bending moment, slope and deflection. Now the boundary condition at a starting station, that is station number 1 or station number 0 for a span 1. Boundary condition that may apply in left hand, that is station 0, is expressed in general form. Ky0 is equal to minus b0, this is equation 1. C theta 0 is equal to m0 is equation 2, where k and c are stiffness constants. So for simply supported end, that means this end is bearing, so there is no deflection, so stiffness is very high, that is k is infinity, and c is a 0. So with putting all the value in equation 1 and 2, we can get y0 is 0, m0 is 0 as per equation 1 and 2. A span 1, a starting station is from the from the station 0. Following assumption is done for part 1. Shear force V0 is 1 Newton, M0 is 0, theta 0 is 0, Y0 is 0. For part 2, assumption will be theta 0 is 1, others are 0. That is V0 is 0, M0 is 0, Y0 is 0. So there are two parts, part 1 and part 2 for assumption. First, span 1. Now mode shape and bending moment, slope and deflection at its last station for span 1. Shear force, bending moment, slope and deflection at any point in the span is a linear function of four quantities and of that span, that is from a starting point, that is 0. So deflection at any point of a span yn is equal to an b0 plus bn m0 plus cn theta 0 plus dn y0, where an, bn, cn and theta 0 is assumed constant. Deflection of shaft yn is equal to yn part 1 into v0 plus yn part 2 theta 0, equation number 3. When yn is equal to 10 for a span 1, yn is 0 because deflection is 0, yn part 1 is equal to yn part 1 because this is 10th station, yn part 2 is equal to yn part 2. So v0 is equal to minus y0 10 part 2 into theta 0 upon y10 part 1. Replacing v0 in equation number 3, general equation for the shaft deflection, yn is equal to bracket start yn part 2 minus yn part 1 into y10 part 2 upon y10 part 1 bracket close into theta 0. Assume theta 0 is 1. So mode shape for general expression, yn is equal to yn part 2 minus yn part 1 into y10 part 2 upon y10 part 1. This is equation number 4. Bending moment, mn is equal to mn part 1 into v0 plus mn part 2 into theta 0. This is equation number 5. Replacing v0 in equation number 5, general equation of bending moment, mn is equal to mn part 2 minus mn part 1 into y10 part 2 upon y10 part 1 into theta 0. Theta 0 is, let's say, 0, 1. Mn is equal to mn part 2 minus mn part 1 into y10 part 2 upon y10 part 1. So bending moment at station number 10, that is last station of span 1, mn part m10 part 2 minus m10 part 1 into y10 part 2 upon y10 part 1. This is equation number 6. Similarly, slope at station number 10, y10 is equal to y10 part 2 minus y10 part 1 into y10, sorry. Similarly, slope at station number 10, that is theta 10 is equal to theta 10 part 2 minus theta 10 part 1 into y10 part 2 minus y10 part 1. This is equation number 7. Now the boundary condition at common point of span 1, 2 and a starting point of span 2, that is station number 10. Similarly, boundary condition for starting station of span 2, k y10 is equal to minus v10, this is equation number 8. C theta 10 is equal to m10, this is equation number 9, where k and c are stiffness constant. This is again, the supports, simply support at this point. So y10 is 0, m10 is 0. If you put in k is infinity and c is 0 in equation number 8 and 9. Boundary condition and common point, that is for span 1 and 2, that is station number 10. Due to shaft discontinuity and common point station number 10, y10 of span 2 is equal to y10 of span 1. This is equation number 10. Theta 10 of span 2 is equal to theta 10 of span 1. This is equation number 10. And y10 of span 2 is equal to y10 of span 1. This is equation number 11. But deflection will be 0. So this will be 0. Both will be 0. Due to bearing reactions and common point station number 10, ky10 is equal to minus v10 span 2 minus v10 span 1 bracket close, equation number 12. C theta 10 is equal to minus, is equal to C theta 10 is equal to m10 span 2 minus m10 span 1 bracket close. This is equation number 13, where k and c stiffness constant, and using the same value K infinity, C infinity, using this K infinity, C infinity at bearing condition. The equation number, equation number from 10, 11, 12, 13, we can write theta 10 span 2 is equal to theta 10 span 1, y10 span 2 is equal to y10 span 1, which is 0, and m10 span 2 is equal to m10 span 1. So these are the condition for station number 10 for both span. Now the starting point for part 1 of span 2 is V10 is 1, M10 is 0, theta 10 0, Y10 is 0. For part 2, V10 is 0. M10 of part 2 will be M10 of part 1, and theta 10 of part 2 will be theta 10 of part 1, and deflection Y10 of part 2 will be Y10 of part 1, but that will be 0. Now the mode shape in bending moment at last station for span 2. Same way we can calculate the shear force at infinite small distance beyond station number 20. We can say is station number 21. So we can write V21 is equal to V21 part 1 into V10 plus V21 part 2 into theta 0 is equation number 14, where station 20 is infinite small distance beyond station number 20 at free end for span number 2. But V21 is 0, and so V10 is equal to minus V20 part 2 into theta 0 upon V21 part 1. So deflection of shaft is written as Yn is equal to Yn part 1 into V10 plus Yn part 2 into theta 0 is equation number 15. So replacing V10 in equation number 15, general expression for shaft deflection for span 2. Yn is equal to Yn part 2 minus Yn part 1 into V21 part 2 upon V21 part 1, bracket close, theta 0. Assume theta 0 is 1. Mode shape Yn is equal to Yn part 2 minus Yn part 1 into V21 part 2 upon V21 part 1. This is equation number 16. Bending moment Mn is equal to Mn part 1 into V10 plus Mn part 2 into theta 0 is equation number 17. Replacing V10 in equation number 17, general expression for bending moment, Mn is equal to Mn part 2 minus Mn part 1 into V21 part 2 upon V21 part 1, bracket close, theta 0. Assume theta 0 is 1. Mn is equal to Mn part 2 minus Mn part 1 into V21 part 2 upon V21 part 1. So bending moment at station number 20 can be written as M20 is equal to M20 part 2 minus M20 part 1 into V21 part 2 upon V21 part 1. This is equation number 18. So this is the equation for last station of span 2. So now the second part is procedures. We'll see how the critical speed is calculated. If the masses are allocated in different station, is 0 to 10 for span 1 and 10 to 20 is span 2, and similarly for diameter, length are also shown here. So simply support a rotor to the one side overhang having two shaft span. One span is between two bearings, another between free and that end bearing. Mass is allocated at different stations and denoted as M0, M1, M2 up to M20. Length of shaft section is denoted as L1, L2 up to L20. Similarly, diameter of shaft section is denoted as D1, D2, D3 up to D20. Now the steps for calculating critical speed. Number of stations are chosen as per convenience, and more the number of stations, the more the accuracy of critical speed. Typically, stations from 0 to 10 are chosen reasonably accurate accuracy for each shaft segment, shaft span. Note that 0 to 10 stations are location of 0 to 10 are location of bearings for span 1, and station number 10 to 20 are for span number 2. Mass of segment and disk are considered as point mass at each station. Mass of shaft segment is equal to density of shaft into cross-section area into length shaft length between two stations. Mass is allocated at each station such that total mass of shaft segment is equally distributed on each side of station. If additional mass is allocated for particular station, then mass is added in that station. Let's say mass at stations are denoted as M0, M1, M2, and M20. Calculate area moment of inertia for each shaft segment, that is I pi by 64 d to the power 4. Unit will be m to the power 4, which is d in diameter of shaft in meter. Calculate flexibility constant for each shaft segment, that is beta is equal to L upon EI. Unit will be 1 upon Newton meter, where L is the length of shaft segment and E is the Young modulus of elasticity in Pascal. Now the span 1, station number 0 to 10, calculation has to be done in two parts, part 1 and part 2. Select the suitable value of angular velocity, that is omega radian per second. Part 1 for span 1, that is station number 0 to 10. Assume initial condition, station number 0. Shear force V0 is 1 Newton, bending moment M0 is 0, slope theta 0 is 0, deflection Y0 is 0. Station 1 is calculated shear force V1 is equal to V0 plus M0 omega square into Y0. Bending moment M1 is equal to M0 plus V1 L1. And slope theta 1 is equal to theta 0 plus beta 1 into bracket start M0 by 2 plus M1 by 2 bracket close, and beta is equal to L1 upon EI1. Deflection y1 is equal to y0 plus beta 1 into bracket start m0 by 3 plus m1 by 6 bracket close L1 plus theta 0 L1. In this way, keep on calculating shear force, bending moment, slope and deflection until station number 10. Now this same span 1 for part 2. Initial assumption, shear test station 0, shear force V0 0, when M0 0, but theta 0 1, Y0 0. At station 1, shear force V1 is equal to V0 plus M0 omega square Y0. Bending moment M1 is equal to M0 plus V1 L1. Slope theta 1 is equal to theta 0 plus beta 1 M0 by 2 plus M1 by 2 bracket close, and deflection Y1 is equal to Y0 plus beta 1 bracket start M0 by 3 plus M1 by 6 bracket close into L1 plus theta 0 L1. In this way, keep on calculating shear force, bending moments, slope and deflection until station 10. Now, for station for 10 to 20, span 2. Again, we need to calculate in two parts, part 1 and part 2. Part 1 for span 2. Initial assumption, station number 10. Shear force is 1, bending moment shear force M10 is 1, bending moment M10 is 0, slope M10 is 0, deflection y10 is 0. Station 1 is calculated, station 11 is calculated, shear force V11 is V0 plus M0, V11 is equal to M10, V11 is equal to V10 plus M10 in omega square Y10, and bending moment M11 is M10 plus V11 into 11, slope theta 11 is theta 10 plus beta 11 into M10 upon 2 plus M12 M10 upon 2 plus M11 by 2 bracket close. Beta 11 is equal to L11 upon I11. Deflection Y11 is equal to Y10 plus beta 11 into M10 by 3 plus M11 by 6 bracket close into M11 plus theta 10 into L11. In this way, keep on calculating shear force, bending moment, slope and deflection from station 10 until station 20. and also calculate shear force at station 21 at infinite small distance beyond station number 20. Now span 2, part 2, calculation, shear force. Initial assumption, shear force V10 is 0, bending moment M10 will be M10 of span 1. Similarly, slope M10 will be slope M10 of span 1, and deflection Y10 is 0, which is equal to Y10 of span 1, which is 0. At station 11, shear force V11 is equal to V10 plus M10 omega square Y10. Bending moment M11 is equal to M10 plus V11 into L11, and slope theta 11 is equal to theta 10 plus beta 11 into M10 by 2 plus M11 by 2, bracket close. Deflection Y11 is equal to Y10 plus beta 11 into bracket start M10 by 3 plus M11 by 6, bracket close, into M11 plus theta 10 into L11. So in this way, keep on calculating shear force, bending moment, slope and deflection from station 10 until station 20, and also calculate shear force at station 21, which is infinite small distance beyond station 20. Now critical speed condition. Bending moment at station 20, M20 is equal to M20 part 2 minus M20 part 1 into V21 part 2 upon V21 part 1, bracket close. So to find the critical speed, find the suitable value of angular speed omega such that the bending moment at the last station, that is station number 20, to become 0, and corresponding value of angular velocity is called the critical speed in radian per second. To convert the critical speed in RPM, multiply with 60 and divide with 2 pi. Select the next higher value of omega such that the bending moment at the last station to become 0, and corresponding value of angular speed is called critical speed in radian per second for higher modes. So in this way, more number of critical speeds are calculated. Now the mode shape of critical speed. Shaft deflection of the shaft span 1, station number 0 to 10. Shaft deflection Y10 is equal to Y10 part 2 minus Y10 part 1 into, shaft deflection Yn is equal to Yn part 2 minus Yn part 1 into Y10 part 2 upon Y10 by part 1. Shaft deflection for station number 10 to 20 for span 2. Shaft deflection Yn is equal to Yn part 2 minus Yn part 1 into V21 part 2 upon V21 part 1. So N denotes number of station, therefore N0 it denotes station 0, for N1 for station 1, and so on. So mode shape of shaft is drawn on shaft length in x-axis and deflection shaft in y-axis for particular critical speed, and this will provide the mode shape of critical speed. Please note that deflection is not the actual deflection of the rotor, but it is a mode shape of rotor for particular critical speed. Now the calculation part. Let us understand with an example. A rotor is simply supported at both end bearing. There is a load of 500 kg at midpoint between the bearing density and elasticity of shaft is 7.8 and 10 to the power 3 kg per meter cube and 2.1 10 to the power 11 Pascal respectively. Shaft diameter is 0.165 and shaft length between the bearings are 1.8 meter and total length of shaft is 3.6 meter. Calculate first, second and third critical speeds. You can see in the figure, and also it has distributed in to a span from 0 to 10 for a span 1 between the bearings and 10 to 20 for a free end, that is span number 2. So actual rotor needs to be transferred into idealized equivalent system consisting of series of discs connected in elastic but massless shaft. Mass of disc is chosen so as to approximate mass of actual rotor. Mass moment of inertia of disk is treated as a negligible, and so the disk mass is treated as a point mass. These are the assumptions. Now for the first critical speed, that is 1375 rpm, calculation is done in the similar way with initial assumptions and you will see the critical speed at its last station, that is station number 20 is 0, which is called the first critical speed. Now the mode shape of the first critical speed, we need to draw the length of shaft on x-axis and deflection of the shaft for that first critical speed at different stations. The mode shape is like this. So this is the mode shape of first critical speeds, where deflection at these two bearings are 0. However, there is a deflection of shaft at other location. Now the second critical speed, which is 3763 rpm, at this rpm or corresponding that angular velocity, the bending moment at the last station becomes 0. Second critical speed mode shape is shown. This is the mode shape for x-axis shaft length, y-axis deflection. This is not the actual meter deflection, but it is a mode shape of the shaft for that critical speed. This is third critical speed, which is 11,618 rpm, corresponding that angular velocity. The bending moment at the last station becomes 0. This is mode shift for the third critical speeds. X-axis is the length of the shaft, y-axis is deflection at stations. There is no deflection of the shaft at bearings. However, there is a deflection at other locations. So I hope you have understood how to critical speed is calculated for simply supported rotor with one side overhung, and there are two spans. One span is between the bearings, another is one bearing and free end. We need to calculate shear force, bending moment, slope and deflection, put the boundary condition, and select the suitable omega value, that is angular velocity, such that the bending moment at the last station, that is station number 20, should be 0. That corresponding angular velocity is called the critical speed. Similarly, select for the higher value and get the higher critical speeds. So hope you enjoy this. Thank you for watching.